For our next example, we've got two workers sliding a 300 kilogram crate across the floor. One worker pushes forward with a force of 380 newtons, while the other pulls in the same direction with a force of 350 newtons. Both forces are horizontal, and the crate slides with constant speed. Hey, constant speed, that's nice. All right. What is the crate's coefficient of kinetic friction along the floor? So this is really kind of showing us just how we might experimentally find a coefficient of kinetic friction. So let's first draw our free body diagram of the situation. We've got the crate. Remember, just a dot. We've got one worker pushes forward with a force of 380 newtons. So we've got a force in this direction of, I'll call that F1. That is 380 newtons, while the other pulls in the same direction with a forward force. Now notice that we have one of them is pushing and one of them is pulling, but on our free body diagram, they are both going to be coming from the object like so, and looking like that, even though one is a push and the other is a pull. This is the essence of a free body diagram. Now, don't forget the weight of the object. If it is 300 kilograms times roughly 10, that'll be about 3,000. So that's, wow, it's a pretty big weight comparatively. In fact, I don't have quite enough room on my board to get the normal force in there. So it goes. All right. One thing I do want to do, though, I'll make those roughly equal to one another, even though it'll be inaccurate for what's happening in the horizontal direction here. In the horizontal direction, one thing we know is that it's constant speed again, so the acceleration is 0, meaning that the net force in the horizontal direction is also 0. And so the force of friction has to be equal to the sum of both of these forces in order for that net force to be 0. Now, in a lot of ways, this equation is, or this problem is very much like the one we just did. Okay? So first off, we're going to get the net force in the horizontal direction, and we'll see that we'll have to use the net force in the vertical direction as well. Okay? So in the horizontal direction, got F1 plus F2 minus the force of friction. So we know the net force is going to be 0 because there's no acceleration. So we can see that the force of friction has to be equal to both of their pushes. Well, we had already determined that just conceptually based off of the idea that it's not accelerating. But you can see how, again, mathematics is the language of physics, and the mathematics tells us the same thing that we got conceptually. The two work together. Now, we know F1 and F2, this force of friction, we know it's the force of kinetic friction, so we're going to have to go with mu k times the normal force is equal to F1 plus F2. And we'll see that, well, we're back where we were conceptually, right? That mu k is a ratio of the applied force to the normal force. You may have noticed, too, that mu k has no units because it is newtons divided by newtons. So there are no units for the coefficient of kinetic friction. Now, once again, we'll have to know what the normal force is, and we'll see, just like we did before, by summing the forces in the y direction, that it is equal to the weight. W, not accelerating up or down. All right, so in the end, mu k is going to be F1 plus F2 divided by mg, the weight of the object. Putting those values in, you should get a value of about 0.23 for the coefficient of kinetic friction.